This theorem is perpendicular to a chord theorem, which tells us that the perpendicular from the center of a circle to any chord bisects that chord. Just like this here, segment OB is perpendicular to chord CD at point A. And as you can see, O is the center of the circle, so segment OB passes to the center and it's perpendicular to chord CD. We need to show that this line bisects our chord CD and show that segment CA here is just congruent to segment DA, to show that this really bisects our chord. So we have here a two-column proof to show the validity of this proof, and this is very important for the next few theorems to be proven here. The first one is, of course, we need to come up with our given. We have segment OB is perpendicular to chord CD at point A. Okay? Or you will want to add here on circle O, so that it is very verified that our O here is the center of a circle. Okay? This is actually given. When adding this statement here, even if it's not part here, we have satisfied the statement that perpendicular from the center, because we are not sure if O is really the center of the circle, but once we have satisfied this on circle O, it's really sure that this passes through the center of the circle. Now, once we pass this notation here, and since it's perpendicular, let's anchor on that. Let's connect the next statement to the idea of perpendicularity. Hence, angle OAC, this angle here, okay, is and angle OAD, OAD are right angles, because that what connects to our first statement, which talks about perpendicularity. Okay, so that would mean our second statement here is definition of perpendicularity. Take note of our end goal. Our end goal is to reach this identity. So we're just structuring all of our necessary ideas here. Which means that the measurement, if they are right angle, the measurement of angle OAC is equal to 90 degrees. This is also true with the measurement of angle OAD. This is a definition of right angles. There is an important proof or a reason behind this, because I need to construct this information as we have our fourth statement, which is very helpful, because we will be constructing segment OC and OD. Okay? We will construct this segment OC and OD here. Okay? And once we do that, of course, this is by construction. Once I constructed that, I have two triangles now. And they are not just any triangles, because of the third statement having one of the angles of each triangle be equal to 90 degrees. Therefore, triangle now, OAC and triangle OAD, this is D, are right triangles. Okay, this is by definition of right triangles. Okay. We need to use this idea because we'll be having the congruence of the two, which will tell us the congruence of these statements later. So this is structured by the idea of perpendicularity, right angles, measurement, and by construction we have right triangles here. Now, for some may not need this, but I just want to show this one for everyone here for scaffolding of information. Okay. Let me continue. Once we have established that, okay, since we have two triangles now, the goal is to come up with triangle congruence. Now, here are the additional statements here. We have here segment OC is congruent to segment OD. Okay. It is said that segment OC is congruent to segment OD here. Why is that? Because they are radii, or before I continue, because I was not able to clarify, or I was not able to introduce radius here, in step 4, I must have here radii. Okay? Construct radii OC and OD so that it's really clear that OC is a radius because of it's what they call this one. It's very obvious because the O is the center of a circle and C is a point on the circle. Same thing with D. So as I introduce that, it's okay for me to do this. So I forgot to do that. Sorry for that. So radii of the same circle are congruent. Okay. So we have established this. Let me take note of this. That one is congruent to this. Okay. Now, what is next here? Since we're talking about triangle congruence, remember the SSS, SAS, and the ASA triangle congruence postulate. We might be using that from time to time. But in this case, since we have established that they are right triangles, we also have triangle congruence for our right triangles. And we have either LL, the HL, and the HA congruence, a theorem. Okay? In this case, let me talk about OA is congruent to OA. This segment here, or side, is a side of both triangles OAC and OAD. So this is for both triangles. So by reflexive property, so they are actually congruent to one another because they are of the same quantity. Now, look at our 6. It's actually the hypotenuse. Both of them are hypotenuse of our triangles. And our statement 7 is one of the two legs. So we can now say, according to our right triangle congruence, we can now say that triangle OAC is congruent to triangle OAD. This is by HL, right triangle theorem, or the hypotenuse leg theorem. This is only true once we have established that the triangles are actually right triangles. We cannot use this if they are not right triangles. But since we are sure on statement 5, and because of these statements that I have established here, this is now true. What is then the purpose of this? Because once we have established that the two triangles are congruent, we can now pick this. We have segment CA is congruent to segment DA. This segment is just congruent to this segment. And what is now the reason for this? Simply CPCTC, or congruent parts, corresponding parts of congruent triangles are congruent. Once we have established that our two triangles, specifically right triangles, are congruent, then all the necessary corresponding parts are also congruent, which is true with this too. So with this now, we have established this identity. But let's not end there, because even if this is what I have provided for you, and this is what was shown by step 9, since the statement here is the center of a circle bisects the chord, okay, it bisects the chord, and we can input here additional statement, and this might be needed, not just this statement here, because this might not tell us that they bisect the chord, but it might tell us, but it's not complete. So this is now the time that we can say that segment OB, okay, bisects, okay, segment or chord CD. That is because of the 9th statement, and this is actually the definition of let's see, since it's the term bisector here, bisector of a segment. Because once we have a bisector of a segment, it divides the segment into two congruent parts. So even if, again, this is our end game earlier, since the statement here talks about bisecting the chord, so we can add this statement, bisecting the chord. These are the complete proof for this theorem, the perpendicular to a chord theorem. So we establish all the necessary conceptual framework before we arrive at the point that the perpendicular from the center of a circle to a chord, and it should be any chord, bisects the chord itself.